Okay, now in the last lecture, what did we do? We started with the colligative properties, and the first colligative property which we did was relative lowering in vapor pressure, right? Which means that when we add a non-volatile solute to any solution, to any solvent, the vapor pressure of that particular solution that is lower than that of the pure solvent, right? And we did this expression, calculated the molar masses of the non-volatile solute. Today we are going to do two colligative properties. The second one, that is known as elevation in boiling point. It is denoted by delta Tb. Right? Now, elevation in boiling point, elevation means increase in boiling point. What is first of all boiling point? When we define boiling point, it is the constant temperature at which the vapor pressure of the liquid of the liquid becomes equal to atmospheric pressure. Right? So when the vapor pressure of any liquid becomes equal to the atmospheric pressure, that is what boiling point is. We have already stated that the lowering in vapor pressure is taking place, right? If the vapor pressure that is lower, when we add a non-volatile solute, more temperature will be required to make it equal to the atmospheric pressure, as a result of which the boiling point that will increase, right? That is what elevation in boiling point is. Now when we are talking of delta B, we say that delta B that is equal to what? That is equal to the difference between boiling point of the solution minus boiling point of the solvent. Okay, if the boiling point of the solution that is taken as TB and the boiling point of the solvent that is represented as TB naught, then delta TB that will be represented as TB minus TB naught. Right? Graphically, if we are explaining this, let's draw a graph between vapor pressure and temperature. Let's say that you know that the temperature, the vapor pressure that is going to increase. So let's say that the graph for the pure solvent that comes to like this. As the temperature is increasing, the vapor pressure is also increasing. So this is the graph for pure solvent, right? And we are saying that the temperature at which the vapor pressure becomes equal to atmospheric pressure is denoted by TB naught. Okay, and then when we add a non-volatile solute, the graph that is seen to come like this. Okay, again for the vapor pressure of the solution also with temperature, the vapor pressure that is going to increase. Now if we see the temperature at which the vapor pressure becomes equal to atmospheric pressure, that is going to be TB. The difference between the two, that is this difference, that is given as delta TB. So delta TB over here is the elevation in boiling point, that is the increase in boiling point when a non-volatile solute is added to a solvent. Okay, so TB is the boiling point of the solution and delta TB naught is the boiling point of the solute. Now if we want to derive a relationship between this, let's derive Ps upon P naught, that is equal to Wb into Ma upon Mb into Wa. This is the relative lowering in vapor pressure, the expression given for relative lowering in vapor pressure. Okay, so we say that if we are taking P naught minus Ps, then what is going to be P naught minus Ps? P naught minus Ps, that is equal to Wb into Ma upon Md into Wa. We have taken this P naught onto that side into P naught, right? So for pure solvent, if we are taking a pure solvent, we say that for pure solvent, P naught and molar mass of the solvent both are going to be constant, right? For pure solvent, P naught and Ma both are going to be constant. So the above expression now becomes what? P naught minus Ps, that is equal to Wb upon Mb into Wa. If we are saying that both are constant, or instead of putting equal to sign, we can put a sign of proportionality. Okay, so P naught minus Ps, that is delta P, and vapor pressure we can see over here is directly proportional to temperature. So we can say that delta P is directly proportional to delta T, or is directly proportional to Wb upon Mb into Wa. Okay, or we can also write that delta T, that is equal to what? Let's say this is the boiling point, delta Tb we are taking over here. So delta Tb will be equal to K into Wa, where K over here, that is the elevation constant. Okay, now to convert this K into molar elevation constant, what will we do? We will multiply the equation by 1000. Right? To convert it into molar elevation constant, the expression will now become delta Tb, that is equal to Kb into Wb into 1000 upon Mb into Wa. Over here, Kb that becomes equal to molar elevation constant, and this expression Wb into 1000 upon Mb into Wa, that is equal to molarity, right? So what will the expression now become? Delta Tb, that is equal to Kb into M, where M that is going to be equal to molarity. Clear? So this is the expression what we are going to write over here. Kb can also be calculated if we know the value of R. Suppose Kb is not given to you in the question. Okay. Kb for every solvent that is going to be different. Water has different value of Kb. Benzene will have different value of Kb, ethyl alcohol will have different value of Kb. So how do we calculate Kb? Kb can be calculated by the formula Kb is equal to R into Tb square upon Lb. Okay, where Lb into 1000. Where R that is equal to gas constant. Okay. Tb that is going to be equal to what? It is the boiling point of the solvent. So if we are taking solvent over here, you can also take Tb naught, right? And Lv over here, that is the latent heat of vaporization. Lv is the latent heat of vaporization of the liquid. Okay, just for example, if you want to calculate it for water, so you put the value of R, you put the value of Tb naught. What is the value of Tb? 373 Kelvin, right? And then the latent heat of vaporization would be given to you in the question, and you can calculate Kb. So Kb for water, it comes to approximately 0.52. Is it clear? So this is how you can calculate Kb. Got it? Okay. Depression in freezing point. Depression in freezing point, that is represented by delta Tf. Okay, and now let's understand what is freezing point. Freezing point is again the constant temperature at which both solid and liquid state coexist. At this particular temperature, both the solid and the liquid state, they are going to coexist. Basically, freezing point is what? When the solid is being converted into liquid. As it starts the point at which it starts converting into liquid, that is known as the freezing point. So at that particular point, the solid state is also going to be there, and the the liquid state is also going to be there. For example, we say that the freezing point of water is 0 degrees Celsius. So at 0 degrees Celsius, both are going to be there. Okay, ice is also going to be there and water is also going to be there. Got it? So that is what the freezing point is. Now freezing point is denoted by delta F, and it is given as the difference between the freezing point of solvent minus freezing point of solution. Okay, so we can write it as freezing point of the solvent, that is going to be Tf naught of the pure solvent, and minus freezing point of the solution, that is going to be Tf. So this is what delta Tf is going to be. If we are explaining it graphically, let's see. If this is the vapor pressure and this is the temperature, so we say that the graph of the pure solvent comes like this. The area below this point, that is the solid, right? And the area over here, that is going to be liquid. At this particular point, both solid and liquid, they are coexisting. So this is going to be the freezing point of the pure solvent, right? So this is what? Tf naught. If we put a non-volatile solute, we see that the graph comes like this, right? Now this is where both are joining, both are coexisting. So this is going to be what? This is going to be Tf, right? So this is delta Tf. Which comes equal to Tf naught minus Tf. Is it clear? So let's derive this also again from Rayleigh's law. It's the same kind of derivation. P naught minus Ps upon P naught, that is equal to Wb into Ma upon Nb into Wa. Okay, again Ma is going to be a constant, pure solvents, and P naught is also going to be a constant. So over here what will we get? P naught minus Ps is directly proportional to Wb upon Mb into Wa. Okay, and P naught minus Ps, that is delta Tf, that becomes equal to, or is equal to K into WB upon MB into WA. Okay, so again if we multiply this by 1000, then what will we get? We will get delta TF, that is equal to KF into WB into 1000 upon MB into WA, where this is known as the cryoscopic constant. Like KB, that was known as the abelioscopic constant or molar elevation constant. KF is known as molar depression constant. This is known as molar depression constant, or it is also known as cryoscopic constant. Right? Now if we say that WB is equal to WB upon MB is equal to 1 and WA is equal to 1000. WB, that is WB upon MB, that becomes equal to 1. WA is 1000. Then in that case delta F, that becomes equal to KF. Right? So what can we say, that how will you define KF? It is the depression and freezing point when WB upon MB becomes equal to 1 and it is dissolved in 1000 grams of a solvent. So in that case your delta TF, that becomes equal to KF. Okay? Have you understood? Okay. Now when we are talking of depression and freezing point, again KF for different solvents, that is going to be different. So we can calculate KF by the formula KF, that is equal to 0.002 into TF square upon LF. Right? LF. So this is what? Then TF over here, that is going to be equal to the freezing point of the solvent, and LF, that is equal to latent heat of fusion. Right? TF is equal to freezing point of the solvent and LF, that is equal to latent heat of fusion. So if KF is not given to you in the question, sometimes it is not given. So KF can be calculated by this expression. Okay? Alright. फिर उसके बाद when we talk of KF, as we said that KF for different is going to be different. The depression and freezing point has many applications. The first application is that it can help us calculate the molar masses of the non-volatile solute which is added. The second is that knowing the freezing point of any solvent, we can make anti-freeze solutions. Now what do we understand by anti-freeze solutions? What do we understand by anti-freeze solutions? We know that in vehicles there are coolants put for the radiator, or we can say water has to be put into the radiator, so that when the engine is working, whenever the engine warms up, that entire water is circulating in the engine so as to control its temperature. Okay? But sometimes what happens in countries where the temperature goes below freezing point, the water inside the radiators may freeze. Right? So to avoid this kind of a circumstances, there are certain anti-freeze solutions which are added to water in the radiators to depress the freezing point, to make the freezing point lower than water. For example, one anti-freeze which we use, that is ethylene glycol. Okay, ethylene glycol is one anti-freeze solution which is used in the radiators, and when we are using this ethylene glycol, the temperature can be, or the freezing point of the solution, that can be lowered. By increasing the concentration of ethylene glycol, we can get the desired temperature or the desired freezing point of that particular solution. Okay, another antifreeze solution which we can use, that is glycerol. Okay, so glycerol can also be used as an antifreeze solution. Another application of this is freezing mixtures. Freezing mixtures. Freezing mixtures are used to lower the temperature. It is generally used for making ice creams or inside the laboratories to make the temperature lower than 0 degrees Celsius. Okay. What is this freezing mixture? It is a mixture of ice and sodium chloride. This is what a freezing mixture is. Right? The temperature can be lowered to as low as minus 33 degrees Celsius by using the freezing mixtures. Okay? So these are the two colligative properties. Now in the next section we are going to do the questions regarding this. Right? Okay, let's do a few questions regarding both the properties, colligative properties which we did just now. The first one, that was depression in freezing point, elevation in boiling point, and the second one is depression in freezing point, right? So the first question is a solution of 2.5 grams of a non-volatile solid in 100 grams of benzene is boiled at 0.42 degrees Celsius, higher than the freezing point of pure benzene. Calculate the molecular mass of the substance. Molar elevation constant of benzene is 2.67 Kelvin kg per mole. So this is a very simple question in which you have to only apply the formula directly, right? Now for elevation in boiling point, what is going to be the formula? Delta Tb, that is equal to Wb upon Mb into Wa into 1000 into Kb. Okay. So delta Tb given to us in the question is 0.42. 0.42, that is equal to Wb given to us in the question, that is 2.5 grams. So 2.5 into 1000 into Kb. Kb given to us in the question is how much? It is Kb given is 2.67 into 2.67. We have to calculate Mb, right? And Wa given to us in the question is 100 grams of benzene into 100. We have to calculate Mb. So let's take Mb on this side. Mb will be equal to 2.5 into 1000 into 2.67 upon 0.42 into 100, right? So when we calculate this, Mb over here, that comes to 158.9. So this was an easy question in which you only have to put in the formula. One question from this section, from the colligative properties, is a definite question in your boards as well as your competitions. So the colligative property numericals are very, very important. Okay, let's go on to question number 2. Question number 2 is what? Question number 2 is by dissolving 13.6 grams of a substance in 20 grams of water. So Wb given to us is 13.6 and Wa given to us over here is 20 grams. Right? Then next, the freezing point is decreased by 3.7 degrees. So delta Tf, that becomes equal to 3.7. Right? Calculate the molecular mass of the substance when molar depression constant Kf, that is given to us as 1.86. Again, direct formula has to be applied over here. Mb, that will become equal to Kf into Wb into 1000 upon delta TF into WA. This is going to be our formula, right? KF given to us over here is 1.86, WB given is 13.6 into 1000 upon delta TF given is 3.7 and WA given to us over here is 20. So this is also a direct question. When we solve this, MB comes to approximately 342.39. Okay, so when we are solving this, MB that is coming to 342.39. This is the second question. So this is again a very simple question. Let's go on to question number 3. What is question number 3? On dissolving 0.25 grams of a non-volatile substance. Now, WB given to us over here, that is 0.25 grams of a non-volatile substance in 30 ml of benzene. Now, in this case, volume of benzene is given to us as 30 ml, right? And density of benzene is also given to us as 0.8 grams per ml, right? So we will have to calculate what? WA. We know that weight that is going to be equal to, or that density that is equal to mass upon volume. So mass will become equal to density into volume. Okay, density given to us is 0.8, volume given to us is 30, right? So this will become equal to 2.40. So the mass, that is, this is what? WA will be taken as 2.40. Okay, then they have said that its freezing point decreases by 0.40. So delta TF, that is going to be equal to 0.40. Calculate the molecular mass of the non-volatile substance if Kf given to us is 5.12. So now you can put in the formula M that is equal to Kf into WB into 1000 upon delta TF into WA. Okay. So Kf is given to us as how much? 5.12. WB given to us is 0.25 into 1000 upon delta TF given to us is 0.40 and WA given to us is 2.40. Right? So when we do the calculations of this, the answer comes to 133.33. That is the molar mass. Got it? Let's go to question number 4. So in this there is a little twist in the question in which the mass is not given directly. You have to calculate mass. Okay? Let's go to question number 4. Question number 4 is again a little different question. So let's see the question first. Two elements A and B form compounds having molecular formula AB2 and AB4. So they have given to us two compounds, one with formula AB2 and the other one with formula AB4. Okay? When dissolved in 20 grams of benzene, 1 gram of AB2 lowers the freezing point by 2.3. So let's write down the denominations given to us for each of the compounds separately. So they are saying for AB2, WB that is equal to 1.0 grams. WA, that is benzene, is given to us as 20 grams. Okay? Lowers the freezing point by 2.3. So delta TF given to us over here is 2.3, right? Whereas 1 gram of AB4. So again WB given to us over here is 1 gram of AB4 lowers the freezing point by 1.3. So WA is also same over here, that is 20 grams, but delta TF is changing. So delta TF over here, that is 1.3 degrees Celsius. Okay, KF is also going to be same because we are taking benzene. So KF given for both is how much? 5.1. Okay, and KF given over here is also how much? 5.1. Let's calculate the molar masses of both. When we are calculating the molar masses of AB2, the molecular mass that is going to be equal to what? WB, which is 1 into 1000 upon delta TF, which is given as 2.3 into 20. Okay, and KF given to us is 5.1. Similarly, let's calculate MB over here also for this thing. So MB over here will become equal to what? Again 1 into 1000 upon 1.3 into 20 into 5.1. Right? So we are saying that MB in the first case, that is coming to 110.86. Right? And MB in the second case, that is coming to 196.15. Okay, so looking at the formula now, AB2 means the atomic mass of A plus 2 into the atomic mass of B will give the molecular formula, na? So atomic mass of A means A plus 2B, that is equal to how much? 110.86. Okay, and AB4, A plus 4B, that is coming to what? 196.15. Okay, let's say this is equation 1 and this is equation 2. So now you subtract equation 1 from equation 2. Subtracting equation 1 from 2. What are we going to get? A plus 4B minus A plus 2B. Okay, that is equal to 196.15 minus 110.86. Okay. Over here, A and A will be cancelled. 4B minus 2B becomes equal to 2B. Right? So 2B that will become equal to what? When you calculate this, 196.15 minus 110, that comes to how much? It comes to 85.29. So you can calculate B from here. 85.29 divided by 2, that will give us the atomic mass of B. This is coming to 42.64. So this is the atomic mass of B, and atomic mass of A can be calculated by any of these. If we are putting the value of B over there, let's say that we are calculating from the first question, the first expression, that is a plus 2b, that is equal to 110.86. ठीक है? So if we are doing this, we can calculate the value of a, right? A plus 2b means what? 2b was equal to 85.29 from here. So a would be equal to 110.86 minus 85.29. Okay? This when calculated comes to 25.57. Got it? So we have both now. We have the atomic mass of A and we have the atomic mass of B. So this is a question which can come in your competitions. What is the next question? 1.355 grams of a substance dissolved in 55 grams of CH3COOH. So we have been given WB, that is equal to 1.355, right? Is dissolved in 55 grams of CH3COOH. So WA given to us is 55 grams. ठीक है? Produced a depression in freezing point of 0.618. So delta TF 0.618. Calculate the molecular weight of the substance. Kf is given to us as 3.85. So this is also a direct question. We know that molecular mass, that will be equal to Wb into 1000 upon delta Tf into Wa into Kf. Right? Wb given to us is 1.355 into 1000 upon delta Tf 0.618, okay, into Wa given to us is 55 into Kf given to us is 3.85. Okay, so when we calculate Mb from this, it is coming to 153.47. 153.47. Right? So this is again was a direct question. Let's go to question number 6. Question number 6 is an aqueous solution of a non-volatile solute boils at 100.17 degrees Celsius. At what temperature will the solution freeze? Now for this we can use a direct formula, that is Tb upon Tf, delta Tb or Tb upon Tf, that is equal to Kb upon Kf. Right? So Tb given to us is what? It is given to us as 0.17. Upon Tf, that is equal to Kb given to us is how much? 0.512. Upon Kf given to us is 1.86. ठीक है? But over here, Kb and Kf, they are given to us in Kelvin kg per mole. So we have to convert this into Kelvin. Okay? So Kelvin में अगर हम लोग convert करेंगे तो this will come equal to 373.17. Right? So Tb TF you can calculate from here. TF will become equal to what? 373.17 into 1.86 upon 0.512. Okay, so when you calculate this, it comes equal to, how much will it come? 0. It is coming equal to that is sorry, not this. How much will this come? 273 minus 0.62.
270.
This much? $272.38. Okay? So there is a depression in freezing point now. Is it clear? Otherwise, what is the freezing point of water? 273.15. So over here, it is coming to 272.38 Kelvin. So you can calculate in this manner also. Right? So let's go on to the next question. Question number 7. Question number 7 is 18 grams of glucose, C6H12O6 is dissolved in 1 kg of water in a saucepan. At what temperature will water boil? Pressure has been given as 1.013 bar pressure and kb for water is 0.52. Okay, let's apply the formula. We have delta TB that is equal to kb into this is our formula, right? Kb given to us in the question is how much? 0.52. Wb is given as 18 into 1000 and Mb for glucose that is 180. Okay, molecular mass for glucose is 180 and they are saying 1 kg of water. So 1 kg of water means 1000, right? So delta TB over here that is coming to 0.052 and they are saying that calculate the temperature of the solution now. Temperature of the solution is what? Delta TB that is equal to TB minus TB naught. Okay, so delta TB given to us is TB we have to calculate and the boiling point of water that is how much? 273. We generally take it as 373. Okay, boiling point of water that is going to be 373. So TB becomes equal to 373.052. That is going to be the boiling point of the solution. Okay? Alright. So let's go on to the next question. Question 8 is a solution of urea in water has a boiling point of 100.15 degrees Celsius. Calculate the freezing point of the same solution if Kf and Kb. This is similar to the question number 6 which we have done. Question number 6 now. So in this also, this you can do it yourself. In this also we are going to use the same formula. Tb upon Tf that is equal to Kb upon Kf. Question number 8. Okay, try to do the question yourself. I am going to explain the next question, that is question number 9. Question number 9 is a solution containing 0.2563 grams of naphthalene, molecular mass 128 and 50 grams of carbon tetrachloride yields a boiling point elevation of 0.201 degree. Okay, while the solution of 0.6216 grams of an unknown solute in the same mass of the solvent gives a boiling point elevation of 0.647. Find the molar mass of the unknown. Okay, now we have this thing over here. The first one we are going to use the formula Kb, that is equal to what? So let's first take it for carbon tetrachloride, CCl4. Okay, so Kb, that is equal to what? Kb will be equal to WTB into Wa into molecular mass of the solute, right, divided by 1000 into Wb. This is what Kb is going to be. Okay, so Kb given to you in the question is how much? We have to calculate Kb. Kb is not given to us. So let's put in the formula, the values over here. Delta Tb is given as 0.201 into Wa, which is given as 50 into molar mass given to us for naphthalene is 128. Okay, upon 1000 into Wb. Wb given to us is 0.2563. When we calculate Kb from here, Kb is coming to 5.019. Then let's go on to the second part. Kb can be used in the second part to calculate the molar mass because Kb is not going to change. Okay, so let's put the formula for the molar mass. That is going to be equal to Kb into upon delta T, I got delta Tb. Okay, so Kb we can see from here. Kb is how much? 5.019 into 1000 into Wb given in the second half of your this thing is 0.6216 upon delta Tb. Delta Tb given to us in the question is 0.647 into Wa. Weight of the solvent given to us is 50. So Mb when calculated by this, it is coming to 96.44. 96.44.